In this recording, we're going to define a new concept called a coset. So we're going to let R be a ring and S be a subring of R. And we're going to define the left coset that is designated as A plus S to be the set of things that look like little a plus little s, where little s ranges over all of the elements of our subring S, and a is just a particular fixed element of R. Now, it's important to realize that there is such a thing as a right coset. A right coset would look like S plus A, and that would be the set of little s plus little a, such that little s is inside S. But in a ring, we know that A plus S and S plus A are exactly the same thing. And we know that because in rings, addition is commutative. So it turns out that these two things are the same set. And so most people will basically talk about simply calling it a coset. So it's important to realize that a coset of S is just written as A plus S, or we could write it as S plus A. But in either one of these, we can think of it as little a plus little s, where little s is ranging over all of the elements of S. And this is similar to, in fact, it is a generalization of the idea of cosets of groups, if you remember that from a group theory class. Well, I want to actually look at some examples of cosets in some of our familiar rings. So I would like, as my first example, to describe the coset. Let's make it 5 plus 8z inside the ring Z. In other words, what we have going on here is that 8z is known to be a subring. In fact, it is actually an ideal of Z. And of course, 5 is an element of Z. So what we've got is that 5 plus 8z is going to be the set of things that look like 5 plus k, where that k is pulled from the set 8 times z. And it's important to realize that 8 times z is just the set of things that look like 8 times something that I'll call L, where L happens to be any integer. And so what we can say is that this particular set, 5 plus 8z, can be thought of as 5 plus 8 times L, where L is any integer of z. In other words, what we've got is x belongs to this set, 5 plus 8z, if and only if x can be written as 5 plus 8 times something, and that actually means that x minus 5 is equal to 8 times something. In other words, x is in 5 plus 8 times z happens if and only if x is congruent to 5 mod 8. So the things in this particular coset are everything that is congruent to 5 mod 8. Okay, well, let's look at a second example. So another example. In this particular example, I'm going to let my ring R be the field of rational numbers. I'm going to let the subring be the set of integers. And I'm going to want to describe the left coset 1/2 plus z. So I want to describe that as a coset of the rational numbers. Well, here again, let's just look at what the definition would say. This would say that I want 1/2 plus k, where k happens to be an integer. So let's think about what that actually means. X is going to be in this set if and only if x can be written as 1/2 plus an integer. And what that actually means is that x is going to be 1/2 plus 2k over 2k. In other words, 1 plus 2k divided by 2. That should actually be just a 2 there. So let's clean that arithmetic up. This is x is 1/2 plus 2k over 2, which is equal to 1 plus 2k over 2. In other words, x is going to belong to this particular coset if and only if x is a fraction of the form odd integer divided by 2. So in other words, this particular coset can be thought of as nothing more than the set of fractions of the form odd integer over 2, where that k happens to be an integer. So to make it just a little bit more concrete, something like 513 over 2 would belong to this coset, but something like 2/3 would not belong to that particular coset. So that particular coset we understand. I want to do a final example. And this final example is going to come from a non-commutative ring. In other words, my ring is going to be the set of all 2 by 2 matrices where their entries are drawn from the real numbers. I will let S be the set of diagonal matrices. So that will be A, 0, 0, B, where A and B are real numbers. This is often called D, the set of diagonal matrices, and I will be using that. And I want to describe the coset 0, 3, 1, 0 plus D. Now, that particular coset, by definition, is going to look like 0, 3, 1, 0 plus something in D, which would be A, 0, 0, B, where A and B happen to be real numbers. Well, when we do that particular matrix addition, we find out that we're going to get A3, 1B, where A and B are real numbers. So if I have B inside this left coset, what that means is that B has to look like a matrix that has a 3 up here and a 1 down there, and it can have any numbers that you want on the main diagonal. So this particular left coset would consist of the matrices that have 3s up here in the 1, 2 entry and 1s down here in the 2, 1 entry. So again, just to look at some basic examples, we would have something like 0, 3, 1, 17 belongs to this particular coset, but a matrix that would look like 0, 1, 1, 5 would not belong to this particular coset. And that is enough for now.